For advanced categorical data analysis, specifically for survival analysis, we split into 2 lectures. First lecture is on non and semi-parametric survival analysis, and the next lecture will be on parametric survival analysis. Okay, so a non and semi-parametric survival analysis basically is a review of the previous topic that we learned in multivariable data analysis. Okay, so this is a review, more to a revision lah, more to a revision on the non and semi-parametric survival analysis. So objective of the lecture, so at the end of the lecture, student understand survival function and hazard function. So there are 2 functions lah related to survival analysis. The first one is the survival function, and the other one is the hazard function. Okay, survival and hazard. So you should be able to interpret hazard ratios and their 95% confidence intervals, and also able to perform the semi-parametric Cox proportional hazard regression. I think I should add one more lah. Able to perform the non-parametric, which is the Kaplan-Meier survival estimator, and the semi-parametric Cox proportional hazard regression. So able to evaluate the proportional hazard assumptions, and if proportional hazard assumption is violated, then we might go to the next one, which is perform and interpret stratified Cox hazard regression. So this is one thing that we did not learn in the previous semester. Okay, so again, revision. What is the motivation for survival duration analysis? We can call, or sometimes we call survival analysis as duration analysis. Okay, analisa jangka masa. In my opinion, duration analysis is maybe is a better term rather than survival analysis, because if you use survival analysis, sometimes people will think it's about survival, you know, death and alive situation, which is not actually. It is a study on duration until an event occurs. So maybe duration analysis is more appropriate. So if you remember, in duration or survival analysis, there are 2 main points of interest. For example, is there a significant treatment effect? Okay, is there a significant treatment effect? How does a medical treatment, for example, affect the time to death? So you have one, time to time, and then second, the event of interest. So you have the duration here, the time. Duration for what? Duration for an event to take place. Maybe death, or maybe relapse. So in this case, duration analysis is about duration taken from a point of time until relapse occurs. Durations of unemployment spells. Okay, how long does it take for the unemployment until the person got a job, and then try to relate with some explanatory variables. We could also look at the rate of risk of occurrence of an event, whether it varies with time or not. For example, does the risk of death or relapse change with time over a period of medical treatment? Okay, so we can see, we can plot the survival functions or the hazard function, and we can look at the risk of death or the risk of relapse or the risk of any other event of interest. If we don't have duration, then we can't use this. Okay. And then if we have covariates or explanatory variables or independent variables, then we can look whether it is related to the explanatory variable. At the same time, we can look at whether the hazard or the survival vary over time or not. Okay. However, there are special problems. I mean, the special problems with survival data actually can be these two. The first one is distributions of survival outcome is highly skewed with non-normal observations. Okay, survival data most of the time will not follow the normal Gaussian distribution. Sometimes survival is, or sometimes the outcome is, is high. It's more common at the initial part of the observation, or sometimes it will be high at the end of the observation or study. So it is it is not normally distributed most of the time. Okay, most of the time. So that poses a problem with survival data, and there are also a problem of sensor observations. Okay, for example, if we do a follow-up study, and until a certain point of time, and we do a follow-up study, and we want to look at whether the patient is alive or not, alive or dead. Okay, and then we follow up the patient. Let's say we got 3 patients. Okay, first patient at 1st February died. Okay, we know that. Maybe how we know that? Maybe the patient did not turn up for appointment. We call the family, and family said he died. He died on the 1st of February. Okay, then we go to our data and we enter data 1st February, status died. The second one, come to our clinic maybe on the 1st of March. Okay, 1st of March, and the last status, of course, when he came to the clinic, he's alive lah. He's alive. So because death is the event of interest, so the status or the event of being survived is considered as censored, because we know that after certain time or in the future he will die, maybe because of that disease. For example, if someone with blood cancer, okay, first month still alive, second month still alive, third month still alive, and then in April, the 4th month, last follow up still alive, and then suddenly did not come to the clinics. So the last follow up, which is 1st of April, is considered as censored, because we know that at certain point of time in future, he or the patient will die because of the blood cancer, but we don't know when. All right, we don't know when. We know that on the 1st of April he's still alive. So because we are not sure when he's going to die, so we label the last event as censored. Okay. So if you look at the outcome of survival data, then you can see that there are 2 components that come together. The first is the event. The second is the duration taken for the event to happen. Okay. For example, if you have event of diagnosis, or a breakdown of a machine, or relapse of a psychiatric problems, then what is the duration taken for the symptoms, from symptoms or from date of from symptom to diagnosis, for example, from production to breakdown, months from diagnosis until relapse. So there are 2 components constitute the outcome of survival data. If we have only this diagnosis, alive, diagnosis, cancer, non-cancer, breakdown, yes or no, relapse, yes or no. If you have only this event without duration, then we can't do duration analysis. Instead, we will do logistic regression, for example. Okay, logistic regression. Censoring is a special problem in survival data. Why censoring occurs? Because of the incomplete observations. Last follow-up, he's still alive. He did not have the event of interest, and after that he's gone. So we don't know when. So it means that it is incomplete observation. If you follow up him for another month and another month, he might get the event. All right. So incomplete observations are the last observed status, which is not the outcome of interest. For example, outcomes rather than death. So this type of incomplete observation is called as censoring. Right. So there are two types of censor: right censor and left censor. Okay. Mostly we will deal with the right censor problems. Okay. Left censor is something that happened before the start of the follow-up. So you might want to read on the concept of left censor. So censoring is a problem in the survival analysis. So we know the survival time. But we don't know the survival time exactly. I mean, for example, those on chemotherapy, right? So we give chemotherapy. We follow up the patients. Supposedly we want to follow up for 1 year. After 6 months of chemotherapy, one of the patient, just left the study. Okay, just left the follow up, and we don't know what happened to him. So we label him as a censor observation. Okay, a censor observation, right? A censor observations. We know that after some time the event will happen to him, but we don't completely observe him. However, for someone who was given a chemotherapy, let's say after 5 months he died, then we know he's already got the event, and he already complete the observations, because he reached the event of interest, which is death. Okay, which is death. If we don't know, then we say that he will definitely lie. He, of course lah, ni ajal maut di tangan Tuhan kan. But we could say that for those who defaulted observations, we know that at one point in the future he will die because of that, but we don't know the exact time. So because of that, we give the status as censor. Okay. So in conclusion, censoring means we don't know the survival time exactly, because he just defaulted, or he just ran away from the study, or he just defaulted the treatment, or maybe he died because of something else, because he died of something else in the accident or whatnot. So really we don't know when is the survival time for him exactly. There are 3 censoring assumptions. Okay. First, censor happen independently. Okay, censor happen independently. Censor are random, and censor do not contribute significant information on data. So this is known as a non-informative censor. Okay. For example, if you have censor that happen due to stopping of treatment, and because of that, when you stop treatment, patient will get severe side effects, and they will just don't come for follow-up, don't come for further treatment. So the missing observation cannot be considered as non-informative. It means that these are censored cases, but they are informative censor, it means that they got something. Why they censor, or why they lost from our study? Because something happened to him due to the treatment, or any interventions, or any conditions. So it is not random, and it is not independent. Okay. So we have to fulfill all these assumptions before we do the typical Kaplan-Meier or Cox proportional hazard or regression. What do we estimate in survival analysis? First, we estimate the survival function, and second, the hazard function. And from hazard function, we can estimate the hazard ratio, or we can convert the hazard function to hazard ratio. Okay, so survival function is given as St, number of surviving pass time t per total number is in sample. And usually one of the parameters for survival function is the median survival function. For example, median survival. Median over survival means the amount of time after which 50% of patients develop or produce the event. Okay, let's say the event of interest is death. When is the time where 50% of patients died? Okay, died. So this is calculated as the smallest survival time for which survival function is less than or equal to 0. Sometimes we are more interested in hazard function rather than survival function. But if you know survival function, then you will know hazard function. Okay, if you know hazard function, then you will know survival function. It's just that you might want to focus on survival, or you want to focus on hazard. We use hazard functions, or hazard function is more commonly used because we are interested to look at the risk. Okay, the risk of the hazard for an outcome, because it is easy to compare groups of individuals. A model based on hazard are convenient for censoring or for several types of failures, and it is easy to compare two exponential survival distributions. And if you know hazard function, then you can convert to hazard ratio. By using hazard ratio, we can compare the risk for an outcome between different levels of predictor. So hazard ratio is what we call written as psi equal hazard at time t for x equal 1 divided by hazard at time t x equal 0. Okay, and hazard are proportional if hazard ratio is independent of time. Okay, if the hazard ratio is parallel to each other, if the covariates are categorical, then we know that the hazards are proportional. Right. The non-parametric survival model, we know this. In fact, we learned this last semester. One of the most well-known non-parametric survival model is the Kaplan-Meier estimator. Okay, Kaplan-Meier estimator. Kaplan-Meier estimator provides a survival estimate. Okay, and from there you can plot survival curve. It is a non-parametric estimate for survival function. We can estimate the survival probability, and then we can plot the curve. Okay. Comparison of survival functions. You can compare survival function between groups. For example, survival functions between male or between men and women. Survival function between patients with non-metastasized lung cancer with metastasized lung cancer. Survival functions between patients on chemotherapy with patients not on chemotherapy, for example. Okay. Survival data are typically right skewed. Okay, and because of this skewness, we use what we call as the rank-based non-parametric test to compare the two survival functions. In fact, two or more survival function. Okay. How to do that? We can show a graphical display of the survival estimate for each group, one for male, one for female, for example, and then by showing the Kaplan-Meier estimator of the survival function. So 1 and 2 ni lebih kurang sama je, and then compare the survival estimate based on some test. Okay, based on some test. What are the tests? Okay, what are the tests? There are actually a number of tests. For example, the log rank test. Okay, the log rank test, the Wilcoxon test, the Taron-Ware test, the Peto-Prentice test, the Flemington-Harrington test. They differ in the use of weight in the formula. Okay, in the formula. I'm sorry, I'm also tak ingat lah formula ni macam mana, tapi they use different weights in the calculation for the contingency table of groups or events. So we are using contingency table, and then we compare the observed and expected observations, and we can use either log rank, Wilcoxon, Taron-Ware, Peto-Prentice, Flemington-Harrington, and in fact we can use all of them together. If there are consistent results, then we know that we are more confident with our result. If the log rank test is very different from Wilcoxon is very different from Taron-Ware, then we might want to check our data. Okay, if data is not that problematic, then the log rank test, the Wilcoxon, the Taron-Ware, the Peto-Prentice, and the Flemington-Harrington will almost be the same. Right. So remember, this is the non-parametric survival model, and we use Kaplan-Meier estimator. So this is maybe one of the earliest survival analysis model. And after that, more advanced model. So we move to regression modeling for survival data, where in regression modeling we can examine more about the relationship of the survival distribution with the covariates. Okay, if we have sex, income, chemotherapy status, marital status, for example, then we can look at the relationship between these covariates with the survival distributions. In Kaplan-Meier, we can't do that. We can, but not that flexible. Okay, not that flexible. So it has limited use. Kaplan-Meier. Okay. Again, when we look at the models for survival analysis, okay, remember, one, we have the non-parametric model, which is Kaplan-Meier estimator. It is not a regression model. And then we have the semi-parametric model. Okay, semi-parametric model, for example, the Cox proportional hazard regression model. So this is a regression model, and the parametric model. Okay, the parametric model. So for this lecture, we are going to focus on the Kaplan-Meier, which is the non-parametric, non-regression model for survival data, and for semi-parametric, which is the Cox proportional hazard regression model. This is one of the most used survival model in medicine and in epidemiology. Okay, very, very commonly used. It is a semi-parametric model. Okay, half lah, half parametric, half non-parametric. So it is a semi-parametric model. Why we say this is semi-parametric model? Because we do not specify the exact distributions of the baseline hazard. Okay, we don't want to know. We don't want to commit to the exact distributions of the baseline hazard. Okay, so we say, okay, whatever distribution of the baseline hazard doesn't matter. Okay, doesn't matter. Right. So if you look at the formula for Cox proportional hazard model, this is written as the log hazard t and x equal alpha t plus the sum of linear combinations of beta I and xi. So the baseline hazard function, which is the alpha t, okay, where we can we can move alpha t to the front and log hazard go to the right hand side, is unspecified. Okay. So this baseline hazard HOT, okay, log the baseline hazard, okay, hazard at time 0, okay, hazard at time 0. We don't want to know that, we don't want to commit the distribution for this, okay. And we have the linear combination, which is the sum of beta I xi. We know about this, all right. So because of this, one is parametric, one is non-parametric, okay. Then we call this as semi-parametric model, okay. If you look at the applied survival analysis book by Hosmer-Lemeshow, okay, I skip the model with no interaction term because we learned that already last semester. So now we have a Cox proportional hazard model with an interaction term. For example, if you look at table 5.1 in applied survival analysis by Hosmer-Lemeshow, we have this variables, and then we have the coefficients, which is the log hazard, okay, the log hazard, and this is age time gender, interaction between age and gender, okay, this one. One thing that you will notice that there is no constant here, okay, there is no constant here, okay. So the formula is written as the log hazard t exponentiations of the linear combination. So and you know that if there is interaction, then we cannot simply interpret variable age and gender, because age depends on gender, gender depends on age, okay. You can interpret BMI, you can interpret diastolic blood pressure, you can interpret about CHF, but you can't interpret as easy as you want with interaction between age and gender. You know that the log hazard equation for age and gender for other covariates equal beta 1 age plus beta 2 gender plus beta age times gender plus other covariates that do not interact. So for female, okay, for female versus male, then we can replace if female is 1, okay, if female is 1, then beta I A, so this will be G female age equal A minus G male age equal A with same covariates. So beta 1A plus beta 2 1 plus beta 3 1 minus beta 1A plus beta 2 0 plus beta 3A 0 plus other covariates, okay. So you'll get the log hazard equations. But if you want to get the hazard ratio, you can just simply exponentiate, okay, exponentiate. For example, if you are comparing someone to population at age 50, female age 50 population versus male age 50 population, okay, female age 50 population versus male age 50 population, then we got this equation. So we exponentiate beta 2 because beta 1a, this one will cancel out, okay, will cancel out. So we got beta 2 1 plus beta 3, and we replace 1 times 50, so beta 3 50, so exponentiate 1.838, which is this one, beta 2 female gender minus 0.027, the interaction term, 1 times 50, because we are comparing female against male for population age 50. What happened to other covariates? Not important anymore because they cancel out each other. Okay, beta prime z minus beta prime z, so you got 0. So the hazard ratio for comparison between male versus female at age 50 shows that female has 1.63 times higher risk or higher hazard for the outcome. Lupa pula apa the outcome dia. So for those who age 50, if you want to know what would be the hazard ratio for age 30, then you replace with age 30 here. Okay. How do we compare survival model? Okay, how do we compare survival model? For non-parametric and semi-parametric model, we can use exploratory analysis of survival data. You can compare treatments or interventions, and later we will learn about parametric model. Parametric model can provide more information, so it is more difficult, it is more advanced. It can provide the estimate, or you can provide the mean of survival time. Non-parametric and semi-parametric cannot provide the mean of survival time. Cannot. Okay, it can extrapolate or predict survival probability. This can also do confidence interval. This one also can give you confidence interval lah. But you know, a parametric model is more special because we specify the distributions of the hazard, and because of that we can estimate the mean, the median time, or the survival time better. Okay, better, right. One so this is something that I know we spent not that much last semester about the interaction, so maybe you can be more familiar with interaction. And something that we also did not spend too much last semester is the evaluations of proportional hazard assumptions. Okay, so we know that this is the log hazard, where the hash not t is the baseline hazard function. Okay, we don't want to specify anything here, so this is not becomes non-parametric. And because of this, Cox proportional hazard regression, one of the major assumptions is that the hazard should be proportional. Okay, the hazard should be proportional. So how to check? We can use graphical methods, we can use goodness of fit test, and we can use time dependent variables in the model. So there are 3 ways to check for proportional hazard assumptions. Use graphical methods, use the goodness of fit test, and number 3, you can add time dependent variables in the model and look at the p-value lah, the p-value of the time dependent variables inside your model. So for example, for graphical techniques, you can plot the log minus log survival curve based on Kaplan-Meier. Let's say you have a treatment 0 and treatment 1, and see whether they cross or not, whether they cross or not. Okay, so in this example, there seems to be a slight crossing here. Okay, slight crossing here. So if at time 3 and below, it seems that treatment 1 has higher value, but after time 3, then treatment 0 has higher values. So it means that the hazard is not proportionate. Okay, it differs. At time 3 it crosses, so it seems to be a slight or a mild violations of pH assumption here. Okay, right. Number 2, you can use goodness of fit test. There are a number of goodness of fit tests. usually what we do is to look at the p-values, even though we have to be careful because p-value is not everything, right? So be careful of the p-values. Look at also the sample size, because p-value is very much affected with sample size. For example, we can run a Cox proportional hazard model. We calculate the Schoenfeld residuals, create a variable that rank the order of failures, and then test the correlation between variables in step 1, 2, and 3. Okay. Fortunately, we don't have to do this. Okay, we don't have to do this. Some functions are available in R, in SPSS, in Stata to do all the steps for you, so you don't have to do this. Okay. So from the goodness of fit test, you can plot. For example, this is variable age. Okay, variable age. So we plot the beta against time, and we can look that generally it looks, I think it looks okay. It looks straight, right? It looks linear. So you can say that there is no there is unlikely violations of pH assumption here. This is for treatment. Okay, this is for treatment. If you look here, there is a curve. It means that for time below 50, the hazard is like this, the log hazard is like this, but after time 50, the hazard becomes like this. So it is going down first, and then after that it's going up. So the hazard is not proportionate over time. Okay, it's not proportionate over time. So from this plot, it shows that there is violations of the pH assumptions. You can use Cox ZPH functions in R, for example, to get the p-value of the goodness of fit test, and also to get the plot. So we will not discuss here. We will look at during our practical how to do that. And time-dependent covariate, time-dependent variable is another way. This is actually by adding the interaction term inside the model, and look at whether the time-dependent covariates are significant or not. If they are significant, then it suggests there is problem with pH assumptions. Okay, so you can do this. Which one I prefer? I think I prefer the goodness of fit test. For example, by using Cox.zph, I can get the global analysis of the pH assumptions. I can use that to plot also the beta against the time based on the Schoenfeld residuals. Okay. If you want to assess a Cox model, very briefly, you look at the Cox-Snell residuals, you look at the martingale residuals, you look at the deviance residuals, Schoenfeld and scale Schoenfeld residuals, and also the F beta. We don't have time to go to this, but every model has to be assessed, has to be evaluated. So you can generate residual. You know that residuals are basically the difference between the observed and the predicted values. So these residuals are basically special type of residuals: the Cox-Snell, martingale, deviant, Schoenfeld, scale Schoenfeld, df beta, and then you can plot them and see how is the model assessment. Okay, right. So now, what if we have this? Okay, what if we have this? What if one of the covariates, at least one of the covariates violates the pH assumptions, proportional hazard assumption is violated? Then one of the remedial measure, or one of the analysis that you can do, is to use stratified Cox model. Okay, stratified Cox model. So for example, we have this plot, this cartoon. This is taken from Clambound. Apalah buku dia tu, tak ingat. Note of the survival. So they run in the book. It shows that in the model with log white blood cell, treatment, and sex, okay, three covariates. So we got the coefficient, which is the log hazard, okay, log hazard, and this is the p-value for the proportional hazard, and it shows that for log of the white blood cell count is above 0.05, so it satisfies the pH assumptions. Treatment is also bigger than 0.05. However, for sex, it looks like there is, crossing of hazard for men and women with p-value of less than 0.05. So it suggests that sex does not satisfy proportional hazard assumptions. So what we can do is we can use stratified Cox by controlling for sex, by stratifying the sex in the analysis. Okay, so we run this in stratified Cox regression, and we get these results. One thing that is very, very important that you would see here is that there is, so variable sex, okay, variable sex is no longer here. Why? Because now it is used, it is adjusted, okay, it is adjusted because it is it violates the pH assumptions. So we use sex, we adjust sex, and what we get is only the log white blood cells and the treatment. Okay, not much difference. Okay, it's quite different. Okay, because you got 1.59, 1.39, 1.39, 0.93. Okay, so we can see here, in particular, we can see the hazard ratio for the effect of treatment adjusted for log white blood cell count and sex is given by the value of 2.537. Okay, the hazard ratio. Okay, the hazard ratio, right. So that's all for